you want to talk of physics? Yes, that's fine.
Mm-hmm.
Questions? Physics?
Our student experiment is due tomorrow.
Yes, you have experiments due tomorrow.
Yeah.
You have drafting something, right?
Yeah, I've finished my draft, but I had questions about validity.
Show me. I will give you. Can you share your screen? I will give you a green light. So what about this experiment? Friction?
We did the force equals BIL prac, and then we changed bits about it, and then we just had to talk about everything.
Yes, that is that will be due tomorrow, right? This assignment.
Yeah.
Which part you are looking for? You got force, inclined motion, right?
This is the electromagnetic force in a current carrying wire.
Oh, that's carrying wire. You measure the force by use balance, yeah?
Mm-hmm.
Okay. What is the question?
How do I justify validity of my data?
Where?
Here. This is like the validity section.
Validity, you have to verify you can justify your result, right? So what is new? You got something unusual? The error is 45%.
Yeah.
Wow.
My thing was, how do I say, I didn't have it, my data wasn't very valid, but before we go,
I noticed the graph is not very the fitting. They got a different variation, right? The maximum, minimum are quite different. How could you get that such big error, percentage error? This one. So I don't think you don't have that big. Can you find the error bar for each point? You only have 1, 2, 3, 4 points. How many? Oh, this is non-linear.
5 points. The error bars are just very small.
It's very small. And obviously, this is not a linear function, isn't it? So you try to, you have to check whether something is wrong with this measurement, especially the last one. So what happened to the last one? How many data points do you have? 5? You only have 5 data points.
5.
Why this last one is lower than expected? Why the last one is lower than expected? If it is linear,
I think it's because we changed the length of a wire.
Yes, well, in that case, one possibility is that if you change the width, another student asks the same question, or I cannot. Can we go to the whiteboard? I show you the probable reason for this large uncertainty, because you are obviously we know that dependence, the formula according to theory. So basically, the theory say, I just copied your data here. So this is a theoretical one. Can we just put this green color? Can we put this green one? We know from the formula it must be linear, right? It's theory. So what the reason is theory, because the force. So you measure the force. Of course, the force is actually equal to the change of the mass. Can you see? I know this experiment. So the wait a moment, change the color to black. Yes, so you measure the force by measure the change of region of the mass, right? And this change of mass, if you multiply the G, will equal to the force, which is proportion to the current, the length, the B, right? So basically, you are simply doing this experiment. So this is a force, right? This is a force you're looking for, right? This is a force, and this is the length. Obviously, this dependence is L. The dependence of force is linear, right? If you put I and B here, that is L, right? So because this time you use the L as a variable. So it's very likely. So this is your result. Can you see? This is the result you show me, right? So this result is obviously not a straight line. Can you see? So therefore, this is not a straight line. So the one probability one is highly possible in this case, okay, especially last reading. So because the length is getting longer. So if there's no guarantee, so according to this formula, every length must be immersed or within the uniform magnetic field. So maybe it's due to the fact that the force, the uniform magnetic force is this much, all right? After that, they become nonlinear, they're getting weaker, can you see? Outside, so you have the, for example, you have bar, you have bar for this, for example, this is north, right? Just have this hypothetical, can you see? So this is the bar magnet, permanent magnet, right? In between this gap is quite uniform. So in this region is uniform. It means that the field is the same everywhere. Can we just highlight this region by, can use this coloring? So it's pretty, so in this region it's perfect, it's almost uniform, all right? However, the field become non-uniform once you go beyond this region, can you see? So that's something you have to be very careful. So of course, if you move far away, they become more, so this is just like a green light, so getting more ununiform, can you see? So in this case, the question is, if you have to check with your experiment, if the length is shorter than this region, that's fine. But for some reason, if the final length is beyond this uniform region, then the force will drop noticeably. In other words, every point of this bar must be within this blue area. Otherwise, you cannot expect the result to satisfy this formula. That is the reason. That is the probable reason. I don't know. Can you show me the diagram you experiment to set up?
I'm pretty sure that's why we had the thing, because our length went over the magnet.
Well, if that's the case, that's the reason. You can explain why.
Say that for validity then?
Well, that's why validity means whether the result is consistent with the theoretical prediction. Obviously, the last one is should be treated as outlier. Alternatively, you can use argument in statistic, right? But if I don't know if you have time to rewrite this point. So you can, no, well, in that case, you can discuss that, okay? You can discuss, so the percentage error is that much because this should be treated as outlier, which you didn't, right?
Because we didn't have enough data points,
Yeah, so that's why if you can see, if you can put your discussion, if we just confine our discussion within this region, and I think the percentage error should be less than 100%, less than 1%. Do you agree? So the R, in other words, if you use this, the R should be, so in this case, if you use this, so R squared will be very close to unit, right?
Yeah.
But if you include that one, so R could be probably just 0.7 or even smaller. Can you see? I don't know what's your R square.
0.93, which I thought was pretty good.
93. Oh, I'm surprising. That's good. So where does your 45% uncertainty come from?
Because when we compared it to
theory,
to this part, we compared the M of this X plus C to M.
Yeah, that is this green color one. Yeah, I know what you mean. So this is this is green. This is the model. So this is the best fit. So this is called the best fit. You see, this is called the best because the computer give you the best fit very quick. Okay.
So we did.
So this formula is come from this formula. So this formula is actually theoretically Why it is
Yeah.
linear? Because of this formula. Can you see?
So because we measured the current and the magnetic field strength,
Yes, that's
we
right.
just calculated that and then compared it to M, and we got a percentage error of 41.
Can I have a look? I stop my side.
Mhm.
That 45% is as overall or just the just part that alternate that last data point. Aha, this is one.
So if we did it here.
Yeah. So the prediction. So they have two M numbers, right? Oh, M. This is a proportionality M, right? It is M in proportionality. This is your best fit, right? 0.1, 0.12 is your best fit, right?
Yeah.
And where is this? Where is this? What does this first equation mean? Oops.
So this is what we got from the graph.
Yeah.
So this is the line of best fit.
That's the best fit, yes. So the slope is 0.12, right?
So we know that in theory it should be M should equal BI because F equals BI. Oh.
Where is 0.2? How did you choose this 0.2 as your reference? Where is this?
Oh, because we measured this. This is T and this is I. No, A.
I can't follow you. What is A? What is T? Current.
As in, yeah, current and magnetic field strength.
Tesla. Yeah, Tesla.
So this is what it should
yeah, so that should be the theory, right? So the first mean or slope is theory. And did you measure? Are you sure you measure the field strength? How did you measure magnetic field strength?
We had a magnetic field sensor.
Sensor? Are you measured by sensor? And that one, double check that is that. It's quite different. If you multiply, it should be very close.
Yeah, that's why we had a high percentage error.
One moment.
We had to talk about that.
One moment. This 0. Can you just multiply 0. I think the field is too strong, right? The field is 0.0. I use your calculator. 485 multiply. Are you sure in M?
Yes.
Not mini M. Any chance?
No, I think it was just the experiment was bad, and we
So
just had to talk about.
So no. This is another issue. You see, from your data, from your experiment data, that variation is not that big. The potentiation should not usually be compared with the best fit and the two extreme. Can we just? Yeah, I don't think your percentage error is not very big. Can you go to the diagram? I show you. Go to the diagram. Show me the diagram. That's very interesting. For some reason, I can't annotate. Is this at PC or?
No, this is on iPad.
iPad. That's right. This happened to another student. Anyway, can we just show me the diagram, because I cannot draw anything. From here, if you want to include the last one, then the result will be quite different. Can you see? Oh, yeah. You really, I don't know how much time do you have. You really have to ignore the last one. If you just spend more,
yeah, but I don't think we can. I just have to be able to
you don't have to
justify it here.
We have this case. No.
I just said it here.
I show you. If you want to accept this high percent uncertainty, that's fine, but you cannot justify within this approach. You see, another error could be due to the accuracy or reliability of measure the magnetic field, which is not easy. Since they have the uncertainty as well. Okay, I know that is not the reason. So therefore, we really don't have much idea about the theoretical slope is, because you have this experiment is not about how to measure magnetic field accurately. Do you have to measure magnetic field?
No, we just did it to make ours more accurate.
No, you set up a reference which itself is not reliable. So how can you say that percentage of error is that high? What you can do is to within the best fit to say the two extreme. Can you stop your sign? I show you how to fix this one. If you really want to discuss, just fix that particular part without a dramatic change, then this is how do you say that. You don't use that. You don't use the reference. This green light. Pretend this green light has nothing. In this case, has nothing to do with this calculation. All right. This straight line is just the best fit without this without outlier. Okay. But this, if you do want to fit another straight line, we can make this another straight line, so which is a variation. Can we do another straight line for you? I still can manage to draw to fit another. Can you see this one? Can you see the white color? Can you see the white color? So this one has taken into account of the last data point. Can you see that? Of course, this is a visual. Can you see? In order to make this compatible or satisfy every data point, I raise this per end. Can you see? And lower this end. Can you see that what I have done here? In order to include this outer layer, which we know which is not reliable. Okay, we know the reason already. Can you see? So what you really have to say in this case, the M, so this is M, so this is M, the best M, okay? So this is M, and there's another one, the lower one, so this one, the zero one is says M prime. It's different. So the uncertainty, the percentage uncertainty, so the percentage error, so that is percentage error is equal to the M take MI divided by M. And these are different slope. Can you see? So these are different slopes. So that percentage I would expect from just from this visual estimate should be less than 5%. Should be less than 5%. All right. From my experience, that should be less than 5%. Instead of 40, it's nonsense. All right. Because what's happened in your case, you have two uncertainty. You have two uncertainty. One is we cannot trust. We cannot trust the measurement of the magnetic field, right? So that field, if you use the formula, that could be quite different from your best fit. Okay, this is just a little bit exaggerated. All right. So this red color is come from your formula. However, we have no confidence about the measurement of magnetic field. You can see it's very tricky to measure field. The sensor, you see, the sensor have proper working area. Can you see? I don't know which sensor you use. If sensor is immersed in that center, okay, that will give you reliable reading. However, for some reason, if you partially put your sensors across this border, and that reading will be different.
Yeah.
You understand? So therefore, we cannot use this one. This will give you another M. Can you see? That is a 0.02 as you calculated, right?
So can I say that maybe I had that low R value because the magnetic field sensor
it's not reliable.
Wrong reading?
Yeah, it's wrong. Yeah, you maybe that the measurement is not accurate enough. All right. So therefore, so even we will take the last data into account, the worst scenario, still the better than the comparison between the best fit and the measurement of magnetic field. Does that make sense?
Yeah.
You can return to your writing. I have a look at your writing. I will stop here. Can you go to that particular part? You see, at this stage, I often suggest students to use the word in the editing mode. So you can write, you can rewrite. Is this editing mode? You can edit that.
Yeah.
So let's read this again. So the experiment had no validity as the experimental results were not accurate. This is over general. This is over general. Can we make it more precise? Okay. The experiment had is valid. Can you say the validity of the experiment is low for two reasons? For two reasons. Okay. Can you rewrite this part? So the
experiment.
The validity of experiment is no. The validity of the experiment is no. The reason, can you start from the reason for, can you guys put in the just English, the reason, or you can say it could be argued that, make it more, it could be argued that the vanity is no. The reason for there are two reasons. There are two main reasons. Can you just rewrite that? It could be argued that there are two main reasons, or there are two reasons. There are two reasons for the relatively low percentage error, 41.04%. Okay, obviously it's very, yeah. There's number one, you just bracket. One is the measurement of the magnetic field may not be accurate due to the inexperience of using the magnetic field sensor.
Interference?
Yeah, not due to the not interference, due to the inexperience in using this sensor, in use this magnetic sensor. We just admit, because every student have pick up some new stuff, right? So that is possible. If you not have experience, and so the field may not be accurate due to the inexperience in using the magnetic sensor. Therefore, therefore, the theoretical prediction, they theoretically calculated slope 0. Right? What is that? 0.2, right? You can check 0.2 based on the measurement of the current and the magnetic field. Cannot be used as a reference, cannot use as a standards. Instead, the slope of the best fit linear function should be used as a reference in calculating or in determining the percentage error. Okay. Okay. And two. The last data point is significantly lower than expected value, as shown in the figure, whatever number is. Okay. Might the perfusion these these may be due to the length of the conductor is beyond the uniform region of magnetic field. We just discussed this reason. Do you agree?
Mm-hmm.
It's due to reason. As a result, it is make that it is as a result it should be considered as the major source of the uncertainty in this experiment. Okay.
Mm-hmm.
Okay, this is two reasons. Okay, this is two reasons.
Yeah.
So this now can we just put another idea here? So that is two reasons. So to work out more to obtain a more realistic percentage error or uncertainty, to obtain a more realistic percentage uncertainty, we can use the following formula. Okay, the formula is percentage error. Can you just use a formula in a new paragraph? Can you just enter?
I'll just write the formula down.
You write the formula down. So that is a percentage error equal to m minus m prime. Okay, you can use wording. You can type in. You can type in a percentage error equal to m minus m prime, m divided by m.
Imply?
Prime, just one m prime is so you m prime just a dash. How does it like derivative m prime? Yeah. Okay. Where can you type in now? Where m is slope. Where m is a slope of the best fit without using the by treating the last data as outlier. And m dash is a slope of the best fitting when all data points are taken into account. Okay, I think that I have some idea now. So what you do, can you stop your sign? I show you what to do next. It takes not much time. And so that I think, so if I, based on my experience, what you can do is that, so can we just draw this diagram again? So you were, wait a moment, color, okay. Yeah, that is you can do, but you have to do some fitting, okay? Because it's easy. Excel do it automatically, right? So basically, can we just draw your experiment result like this, all right? And the last one is like this, something, a little bit of exaggeration, all right? Exaggeration. So what you can do, you can use this, you can do the fitting without last one, can you see? And then another one is using the old data. Can you see? You do it twice. Can you see? Do you understand? So therefore, then you can get more realistic fitting. So basically, this is, can you see? This is proportional to m, right? And this is proportional to m dash, all right? You understand? So that percentage error will equal to m take mi. Oh, that's probably just this way. M dash take m divided by m. Can you follow me now? So this is the green one. The green one is the best fit. I think the R should be very good. R square should be very good. You try it, all right? Can you see that? Can you see that yellow square? So therefore, in this case, I expected that if you just exclude the outlier, then R square should be very close to 0.99 even, all right? But this should be not too bad. So this R should not too bad. This R square should be larger than 0.8, all right? Did you mention 0.8 somehow?
R squared is 0.93, so I talked about it, yeah.
Okay, yes. So therefore, if you substitute these two m value, I expect that this percentage should be less than, say, 5%. Much better than this number, you see. So you got 40-some%, right?
Yeah.
Can you follow me? So ignore this red color because you have no confidence. We have no confidence for this measurement, all right? So as a whole, it's not bad. So that is that explaining everything. Do you agree?
Yeah.
The reason you can justify, you say your teacher will say, why, how can you justify to treat the last one as alternator? Because you say that it's significantly below this linear prediction. And with the high, because it happened to be, this is the longest, can you see? This is the maximum, can you see? So this is a minimum. So this is within the range, can you see? Maybe when the air extends this point, it is outside the uniform. It happened gradually. You say, can you see they have a uniform distribution inside, right? So maybe your length, can you see, is the length of bar at the beginning when this minimum, okay, this is maximum. Can you see that? So obviously the last one should be excluded. So therefore, if you do want to take the reason which take all into account is that before we understand this reason, so therefore we work out the R square is about this much, right? Oh, what is slope? What is the slope of can you look at your diagram? What is the slope when you do the fitting, including all data point? That would be interesting.
Oh, that's 0.1201.
0.12, yes, we're slow, we're low, much lower, right? It's lower than that. Can you look at your writing? I can't remember the number now. You can share your screen. So where's your report? Okay, scroll up, go up. Yes. So yeah. Okay, it's diagram. Yeah, please stay with diagram. Okay. Can you see that the feet of the 0. Can you see? Oops, disappear. Okay, can you stay here? The solid dark line, the darker the solid line, the slope is 0.12, right? The slope, and the R square is.
That's for this one.
Sorry.
The slope, the 1.2 is for this one, which is the line of best fit.
That include all. That include all data point, right?
Yeah.
How about the solid line slope?
This is the max one, and this is the min.
Oh,
so the maximum trend line.
Yes. Alternatively, you will work out this uncertainty in slope to calculate the relative. Yeah. Yes, okay, please do that. So I think, okay, what I suggest to, because you can get even better R square by ignore the last data, all right? Forget about last data and to find another fit, best fit. Okay,
Yeah.
that would be the reference. Oh, hang on. In this case, the dashed line is your model, right? The best fit.
Yeah.
Well, if that is so, you can just another thing. Can we go to yeah, I follow your line. Can we just go to the alternatively, what you can do is if a follow you have done, you don't want to change too much. So what is your case is that yes, so this is so you have the 5 data. So 1, 2, 3, 4, 3, something like that, right? So you have the best fit already of everything, right? This can we just use the green color? That means so the best fit. So the green one is the best fit of everything, right? And on which you got 2 extreme case. One is the minimum, right? One is the minimum. I don't know how to ever. I was trying to draw this minimum. So one is something like that, right? Another is something like this, all right? You agree? So therefore, you got the in this case you can do this by arguing that this is not a different approach. So the percentage error will be equal to the delta, or will be the m maximum, right? Take m minimum, right? The slope divided by the best fit. Can you see? So this is the best fit. So this is the best fit, all right? So this is a minimum. Can you see? You can use can you see? This is a maximum, right? So use this formula instead, please, if you don't want to change too much. But don't use that formula, okay? The reason the percentage is too high because you use this formula, right? F equal to BL, BIL, right? But this is not, that is the reason the percentage is high, okay? You say up to you, I don't know. So tomorrow is due tomorrow, right? Well, in that case, if you don't want to spend too much time, you just stick with this the presentation. Okay. My suggestion would if you follow my suggestion would take a longer time, but you can ignore, right? But this is something important. You have to mention it. You maybe have to draw similar diagram to communicate with readers. All right. The longer the conductor, the probability is higher for that. The chance is high to the field is not uniform anymore. Okay. Any other questions? So how long does it take? Take weeks, several weeks now? This
yeah, it's been several weeks.
Yes. Well,
I thought I had it done well, but then when I had a class today and
yes, I think if you show me this earlier, I can punish your drafting. But still, can you just show me? You read it now, and we see if we can do some adjustment for your writing, or do you know what I mean? If this is your final draft, you can I give you a little bit of tuning or comment, right? Can you go back? Can you show me the beginning? What is the title of this report? Factors affecting the electromagnetic force experienced by a wire. So that is decided the title, right?
Yeah.
Magnetic field factor as a yes, okay, rational. This experiment aim to determine. Can you read now?
This experiment aims to determine how the length of a copper wire affects the electromagnetic force experienced by the wire.
The same wire,
experiment-
the same wire, right? It is the wire is the conductor, the copper wire. Okay, okay.
The
Oh
original
no, sorry,
experiment.
no, that's my question. Yeah,
Oh.
okay, yeah.
Mhm.
Can we just give you some remark? The experiment is aimed to determine. Can we, if you wish, this experiment is aimed to determine the dependence of the electromagnetic force on the conducting wire on its length. Dependence of the magnetic field on acting on a copper conductor on his length. The original experiment measured the force experienced by the force when current is varied. In the original experiment, no, I don't want to change too much. Okay, just some. It expected that the data would reflect. It was expected that the data would reflect a theoretical relation. It expected that the data would reflect. It expects the measurement would be consistent with the theoretical. Can you see? It expects the experiment would be consistent with the theoretical relationship. Okay. Where blah 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 is from. Okay, so where F is a force. I don't have much time. See, you can no indent when you say where. This is continuous wording. See, whenever you explain the letter, yeah, no indent. Okay. And Burns over derives its Q. Suppose that supported by that. Okay. Can you read it out? You can improve your writing by reading it out to someone. Yes.
Well, the relationship F equals BIL was supported by the data from the original experiment. A high percentage incentive was calculated, indicating low reliability.
Where?
The original.
So you found this error before in your previous experiment, right?
That was percentage uncertainty, not percentage error.
No. Are you talking about the original experiment? Are you talking about this result?
From the original.
Oh, so you encountered this high percentage error before, right? Wow. Relation was supported by the data from the original experiment. A high percentage uncertainty was calculated, indicating no reliability. You are talking about previous experiment. Oh, that happened again. So we have another reason. Probably the sensor is cheap. It's not very good. It's not good enough. It's not sensitivity of this. How to say, the sensitivity of the reliability of this sensor is not very high. You see, you encountered twice, right? Yeah. Practical give you some fine tuning was supported by the data, while the relationship was supported by the experimental result. Can we data? Yeah, this is mathematical terminology. Experimental result from the original experiment. But can you put the but? Okay. But can you delete this while? Just the relationship is no, but the high percentage was obtained. And hence, yes, suggesting or indicating, doesn't matter. It can say no in reliability. The original experiment assumed, can you read original experiment?
The original experiment assumed the value of the magnetic field strength to be constant and kept the length of the wire constant, as the effect of the length was considered negligible. However, due to the imprecise nature of the results, the effect of the length of the wire will be investigated to mitigate sources of error.
That is the reason you did this experiment, right?
Mm-hmm.
Did you do any, or you change the variable, okay?
Yeah.
Can we say this is not logical? Can we delete this, however? Can you see? To further understand, to further understand the nature of the magnetic field, okay? To further understand the dependence of the force on the length will be investigated this time. Okay. You see, this is more smooth. This is more logical. Okay. And okay, so let's go next one. The experiment modify the original by recasting the origin by redirecting the investigator's effect of length of well, but also change the matrix. Yes, that's more specific. Okay. Okay, let's go to the third paragraph. Experiment assume, please.
That the magnetic field strength be
no,
constant.
The experiment. Can you read the experiment? Assume that
the experiment modifies the original experiment.
Assume the experiment assumes that magnetic field, the third paragraph. The
magnetic field strength B would remain constant at the measured value of 0.0485 T.
Tesla,
as the fluctuations in the magnetic field strength could not be accounted for in the theoretical relationship. It was also assumed that the angle between the wire and the magnetic field would remain constant at 90 degrees, as the magnetic field direction could not be measured. The current was also assumed to remain constant at 4.2.
But can you say 90 degrees as the magnetic field direction could not be measured? Could not precisely determined. Could not precisely determined. Yes, you are not dealing with ideal uniform magnetic field, right? The current was assumed to remain the parameter in case fluctuation. Okay, let's go to next one. Next page. Therefore, please read.
So this is that's like just a link to the research question.
Yeah, research questions. Can you read that? What is the relationship here between the length?
Between the length of a copper wire perpendicular to a magnet increased from 0.02 to 0.10 meters in 0.02 meter increments, and the electromagnetic force experienced by the wire when the
that's a research question. Yeah, that's a research question. Okay, that's what's the methodology. The original method measure the force.
This one isn't as important. We don't get any marks for it. Okay. Our teacher just said to include that. This is the part that's like.
Oh, this is just formality, right? Let's go to the. Let's go to your result. And
the modifications is important.
Oh yes, can you make sure? So what is difference? What is the first modification? Extension, increase the range of the length of the first. Yes. So increase the length. Can we say adjusting? Because you probably you can actually, you don't have to from the original length in your first experiment. You can start it from shorter. Can you see? Perhaps that is the reason you just make it longer, right? Actually, you can start it from even shorter length, but obviously you didn't, right? Okay, that's fine. How about the second? After redirection?
Changing the independent variable from current to length.
That's right. Yeah.
Is this justification right for both of these?
Well, what is your justification? Well, if you don't change the length at all, then you wouldn't get that dependence. Because there are the. Do you want to check your justification? Did you mean you want to just check which one? You want to read the second column, second row? Are you going to reflection? Do you want to
this part?
Yeah. Can you read that justification for redirection?
Length was not considered in the original experiment, and the results had a high percentage uncertainty. Thus, the length is now investigated.
And had a high percentage error uncertainty. Is that logical? That
I'm not sure.
Because can we suggest the length was kept? Can you say the length was kept constant in the original experiment? Okay. In the original experiment, the result of a high percentage uncertainty. Okay. You think that I can hardly understand your rationale, because you think that length is variable, or that the length is now investigating independent, right? Then was treated was kept constant original experiment. Can we just delete that the result had the high percentage uncertainty? It is now, yeah. Result, but the length was kept as original constant experiment. Okay. Yeah, you just delete it. Okay, let's go to the refinement.
Refinement's not that important, I think, because that's easy to justify.
Okay.
Do you think this part is a logical conclusion?
Which one? Can you highlight that part?
Buff length is now investigated in an attempt to produce better results. Can I justify it more?
No, to not so can you just put it that way? Can you say the length was the keeper's original as the yeah, and I had idea now. So can you say the length was kept constant in the original experiment period, okay, as a period. The second sentence is as the result, as the percentage error was high, was it high? It is necessary to exclude the how to say, it's necessary to find out the origin of this observed of this uncertainty by studying the length, by how to say, because the idea is that because there are only three variables, right, in the formula, current, magnetic field, and the length. All right, if we can, so this is not original writing, this I just explained to you. If we know that the length has nothing to do with this origin, with this observed large uncertainty, then we can be more confident that the high percentage error is due to the uncertainty in measuring the magnetic field. Okay, can you put some wording for that? As the percentage is high, it is necessary to know the origin. It's necessary to know its origin, right? Period. It's to know its origin. By studying the length, by studying dependence of the force on the length, this the source, the range of the possible range, the how to say, the range of the unknown, the range of factor will be reduced. I hope you will also discuss in your in this draft that indeed, because this time we have studied another variable in which that still high percentage error still exists. Therefore, that is must due to the measurement of magnetic field. So something you have recommended that care must be taken at the end of this writing. Care must be taken in using the sensor for measurement of magnetic field, right? Because you have repeatedly shown that the percentage error is high. And also it is unlikely to make the terrible mistake to in measuring the current, right? The current is easy to measure, right? You just use ammeter, right? The digital.
Yeah.
How could you make the terrible mistake? So I think put everything together. You can, I think, I spend some time to put everything together. That at the end of this conclusion, you can mention that can we go to your in conclusion now? Can go to your conclusion? The end of your discussing. Yeah. In your conclusion, I suggest you mentioned that the uncertainty should be significantly lower without using the theoretical formula based on the measurement of magnetic field. So this is something very important to tell the people in the future, right? Otherwise, they will repeatedly make this and also suggesting your school buy more expensive equipment.
Yeah.
I'm laughing when I saw my daughter use this apparatus. I said, this is a toy. It's not this is not a physics measurement.
Yeah, it wasn't that great.
No, other school use better digital equipment than your school.
Mm-hmm.
But of course, you say very nicely. You don't be so critical. Yes.
Improved by using better equipment.
Without using improvement of the extension. Find more improvements, find a more reliable method or equipment to measure the magnetic field. Okay.
Mm-hmm.
That is a improvement extension. And also, but this is secondary. The prime improvement is that to make sure that the length is vary from the shorter to reasonably longer. You see, if you want to increase from the original length, and the chance is high to go beyond the uniform region. Do you know what I mean?
Mm-hmm.
So therefore, for example, if the length is 5 centimeters, right? Originally, it is better to start from 3 centimeter and then reach to 5 centimeter instead of go from 5 centimeter to 10 or to 8 centimeter. Do you know what I mean?
Mm-hmm.
So this is something I noticed. Yeah, you could include in your discussion.
Yeah.
So I think that is the main reason. So there are two reasons. One is you have in both original experiment and the current experiment that to show indicating the measurement of magnetic field is not reliable or not reliable. And two, instead of increase the length, we should, people should start from a shorter length. In that way, you can avoid that outer layer, you see?
Mm-hmm. Yeah.
Okay, that's probably what we can do this time. But next time you can send your draft earlier to me, all right?
Yeah, I'll send you my research investigation.
Yeah, next time when you have the assignment, let me know, and maybe I can involve in your measurement, right? If you don't have proper data, how can you get the good result? You see, so we can start it. Yeah, we can discuss this kind of assignment earlier next time. Doesn't matter. So if you feel fine with a specialist, fine. Sometime we can talk about more about the physics. Up to you. Right.
Yeah.
Okay.
Thank you. I'll see you on Friday.
Okay, see you Friday. Goodbye.
Bye.
Bye.